Hello everybody, how are you doing? This is Professor Carlos Torres-Verdin broadcasting for Principles of Formation Evaluation. Today we are going to introduce a very important topic, which is the integration of well logs and core data. This integration is very important for a number of reasons. Number one, well logs have several important limitations. They have a lot of very good attributes. They are in situ, they are continuous, but they also have some limitations that we need to take into account when moving toward the interpretation of well logs into petrophysical properties, storage and flow, geomechanical properties, compositional properties, geophysical properties, any physical property that we want to extract from the combination of well logs. Second is that there's not one well log that tells a complete story. We have to combine multiple well logs, multiple physics, in order to be able to come up with a unique, integrated, robust interpretation of properties of rocks. So because of that, we have to use what we call effective medium theories or interpretation methods, or what some people call them interpretation models. And all of those models are based on assumptions about the properties of the rock, whether the rock is homogeneous, slightly heterogeneous, isotropic, a number of properties. And all of those methods, models, they have their unique parameters. For instance, Archie's equation has the parameter for an exponent for porosity, an exponent for water saturation. And those parameters, they need to be adjusted. So because of that, we need to have a reality check. We have to have independent verification of all of these assumptions. So because of that, it's very important to always do the interpretation of well logs, understand their limitations, and based on those limitations, understand how the variables need to be adjusted or the methods need to be adjusted so that at the end of this process, the results are consistent with the measurements we can make on core samples. And one of these ideas is to do core log integration, in the sense that we have the logs and we have the core samples, whole core samples or slabbed core samples laid out on tables. And we walk through the tables and we bring the logs and we compare the logs to the core samples. Of course, we have to be mindful of the differences in depth. We have to correct for depth. We have to correct for volume of investigation of the different well logs. All of those things they need to do. But it's very important because one has a picture of the variability of properties that the rocks have, then it's much easier not only to interpret the well logs, but also to understand how these properties can be extrapolated to the scale of an outcrop. That's a very important point. So we are going to cover this. This presentation is a continuation of several video lectures that I've had on principles of formation evaluation, which can be accessed from my YouTube channel. They're ordered. You can go through them. In fact, here I have an image of how to access the YouTube channels. Please go ahead and see some of these presentations. You are going to understand that the material is very similar from lecture to lecture. All the lectures are building up on the previous lecture. And there's a way to, we have exercises, we have objectives, we have questions, summaries, all of that. So please go ahead and read through those lectures. Concerning this particular lecture, what I'm going to do is I'm going to break it up into 3 parts or 4 parts. And the first part is going to be the introductory part. This is the introductory part. And I'm going to show you that the main objective here is to describe the super basics of the qualitative process of well log core integration. Then we are going to understand the differences and the complementary elements of core samples and well logs, especially core laboratory measurements. We're going to, as the main part of this lecture, we are going to look at three types of clastic rocks, three types of core samples laid on tables. One is a classic sedimentary sequence, is a turbidite sedimentary sequence. The second one is a carbonate sequence in the Permian Basin, and the third one is a hydrocarbon bearing unconventional rock, which is Eagle Ford shale. Those examples are very interesting because they cover different aspects of the complexity of rocks, and they give us a very good idea of the integration and differences in complementarity of well logs and core data. So here we are, those are the objectives, and let's start moving. The introduction. So I'm Professor Carlos Torres-Verdin. I work at the University of Texas at Austin, Hildebrand Department of Petroleum and Geosystems Engineering. I do formation evaluation, reservoir geophysics. I do rock physics, petrophysics, computer methods, analysis, inverse techniques, image theory, and some artificial intelligence, deep learning, data analytic techniques. We begin by understanding that any interpretation method that we use to interpret well logs, borehole geophysical measurements, has to holistically incorporate all the notions that we have about the genesis and diagenesis of the rocks and how the fluids are there. So we have in our mind to be able to bring the geometrical context, the geological context, and also all the principles of measurement that we have for well logs. So if the end product of the analysis is to establish storage, flow properties of rocks, mechanical properties, electrical properties, nuclear properties, magnetic resonance properties, acoustic, dielectric, etc., all of those things, we need to understand the physics of them, and we need to understand how they're intermixed to produce estimates of the properties of the rocks. And so because of that, it's very important that in all of these methods of interpretation, we integrate the complementarity of well logs, core samples, and outcrops. All of this is going to give us a very good picture of the geological and physical reality of rocks for whatever purpose we want to use them for. So the outcrop scale is very important because if one is working in the geohydrological business, looking for water, or one is working, for instance, in soil remediation, or one is working on hydrocarbon reservoirs, it's very important to understand the basic scale that controls the flow properties. Or even for geophysical measurements, seismic amplitude measurements, is very important to understand the context, the volume of investigation, if you will, of all the measurements, and what is the representative scale of the measurements to predict, for instance, flow between two wells. And that's the reason why it's important to understand this very scale and the variability of rocks in that scale. And that variability, of course, will change and depend on the particular type of rocks, be them clastic rocks, carbonate rocks, unconventional rocks, combinations of all of them, and also in the context of geomechanical deformation, the effect of drilling, for instance, the effect of fluids migration. All of those properties are very important to understand in this very context. But for the context of well logs, it's very important to also understand the rocks that are penetrated by wells. And when we drill wells, there are several procedures that one can use to retrieve samples of rocks. One is to have a drilling system. It's a cylindrical system that actually cuts the rocks, takes cylindrical samples of the rocks at the same time as perforating with a given diameter. The example that I'm showing here, which is a pizza box that has several samples here, is several cylinders, is that the diameter of these samples is 3 inches, 3 inches of diameter. And then the rocks initially were cylinders, but then they were slabbed, cut, so that they expose a flat portion of the rock. If you turn these rocks upside down, you will see the cylindrical side on the other side that we don't see here. And of course, the samples here break because they naturally have a tendency to break once you bring them to the subsurface. They are no longer stressed. They are no longer under in situ stress conditions, and that releases some of the fluids. And there are several different ways to preserve these rocks. Some of them are preserved under very low temperatures. Sometimes they have a paraffin cover. It really depends what you want to do with them afterwards, to do analysis of the fluids, analysis of the petrophysical properties. So in some cases you want to preserve the fluids in the rock and so that they look the best possible as they were in situ original conditions. But here we have these samples that were retrieved from the drilling process. These are called whole core. And what you see as part of these cylinders, these little plugs, is that actually after slabbing the whole core, the cylindrical sample, people do different things with the two parts that are slabbed. One is done for geological, geochemical, chemical analysis of various kinds, and these plugs are done so that you take a plug about 1 inch diameter and maybe 1 or 1.5 inch or 2 inches in length. And why? Because you are going to take those plugs and do measurements, and then laboratory measurements for porosity, permeability, capillary pressure, electrical resistivity, relative permeability, sometimes even for geomechanical properties, for a number of things. And then those measurements constitute the basis of the reality checks that we do when interpreting or complementing well logs with that. And so those are the marks. The other thing that I want to point out in these pizza boxes is the values that you see here, 7693, 7695, that's the depth in feet. But it's very important that we understand that depths are measured in different ways. When you drill, you measure depths using the drilling subs that are coming as part of the drilling bit. So you just stack them, measure each one of them, and multiply by the number of them, and that's how you get the depth. And then these are marked. Whereas in wireline logs or LWD logs, we have different ways of measuring of depth. In the wireline open hole domain, depths are measured with the length of the cable subject to corrections because of tension. So we have all of that. Now, in addition to that, to properly understand the variability of rocks, these are actually rocks that come from a clastic sedimentary environment. That means that they came from a grain pack. They have different variability. They have sandstone shale laminations. They have fractures. They have marks, rippling marks. Some of them have clasts like this. Some of them have fractures. Some of them actually have marks of bioturbation. So it's all of this happens because these rocks, we have to remember that they were deposited and formed over many thousands of years. And many things happen over a period of thousands of years and the cycles of the earth. And that's the reason why we have variable conditions. And bottom line is that because of these variable conditions, the rock itself will have different properties at different scales. It would be nice if all of these rocks were homogeneous because it will be very easy to predict all of the properties. Those properties will be independent of size because for any size you will have the same properties. In addition to understanding these properties at the scale of this whole core, very often we take what we call thin sections. These are very tiny sections that we take out from the rock and we slice them on the rock, and then we place them on a glass surface. We call them thin sections. And then when they're on the glass surface, we looked at them through a microscope. And these slices of rocks, very thin slices of rocks, are glued to the glass with epoxy. And the epoxy comes out in the microscope as this bluish figure. But if you look at these rocks under the microscope, and these grains can have anywhere between 150 microns to the side, 200 microns on the side, you can imagine what the size of the pore sizes where the fluids will be. But that gives us an indication of the constitution of the rocks. These are clastic rocks, as I said, because they're grains, packs of grains. Even though we don't see the grains at the scale of the whole core, if you slice it, you look at it at the microscope, you're going to see the grains, and you're going to understand why these rocks can store fluids, and second, why these rocks can allow the fluids to move through them. And that's important for any endeavor that we have having to do with fluids in rocks, for geohydrology, for hydrocarbon reservoir characterization, for contamination, geothermal. All of these are very important domains that require the understanding of storage and flow properties of rocks, not to mention civil engineering foundation studies, mechanical properties, and if you are trying to look at these rocks with geophysical methods from the surface, remote sensing, then you have to understand what the different properties are: electrical conductivity, acoustic, elastic properties. All of those have an influence. Now, the other thing that is done of these rocks when they are cylindrically cut, and this is a cross-section, is that the rocks very often are X-rays. They're X-rayed. And so they're introduced into a machine that X-rays them. And when you X-ray them, you can understand variabilities inside them that are not visible from the surface. For instance, pore sizes, fractures, variable composition, things that are easily seen by variations of density. So this is one of the things that we have. And again, the diameter here is the diameter of the cutting drum that was used to produce the samples during the drilling process. It could be a common size is about 3 inches in those pizza boxes that I show you. And now that's what the whole core is. But as I said, retrieving whole core from a well is very expensive, very, very expensive, because it demands specialized equipment to retrieve them. And because of that, we cannot acquire them continuously over long distances along the well trajectory. And second or third, once you bring those segments or whole core samples to the surface, then they no longer represent in situ conditions. So because of that, we have well logs. These are continuous measurements of multiple physical properties that together allow us to understand every single aspect of the rocks, their composition, their petrophysical properties, storage flow, the geophysical properties, physical properties. All of those are going to be merged with an interpretation technique. So here we have, for instance, a gamma ray log, the spontaneous potential log, electrical resistivity logs with different depths of investigation. Then we have the neutron density and photoelectric factor. Then we have the P wave velocity and the shear wave velocity or slowness. And then here we have calculations of porosity, calculations of saturation over here. And because of that, to be able to do these calculations, we have to have also some reality check with core data. So the dots that you see here are measurements of porosity here, permeability here, and water saturation here that were done on cylindrical samples. So those samples that we saw before that are taken as blocks from the whole core, they are sent to the laboratory and all of these measurements are made. Many of them, a multitude of them, each one of them is one of the dots here, and together they allow us to bring a perspective of whether the calculations performed with well logs are accurate or not. Of course, sometimes they're not accurate because the measurements are not sensing the same property, but you can imagine how well, you can see how well they match porosity, relatively well, how well they match water saturation, and permeability maybe not so great, but it's very close. And based on those analyses, by merging all of them, because not one well log gives you all of the properties, you have to combine them, then we can estimate porosity, permeability, compositions. Here are the compositions, shale, sandstone, and so forth, so on. And this well log is called magnetic resonance, and I mentioned that in some of my previous video lectures. And all of these logs are acquired with instruments that are lower in the borehole. And those instruments work with different physics. We have to combine them, and because they work with different physics, they're going to be looking at the rock in different ways, different volumes of investigation, different resolution, different effects on the fluids, different effects on the solids. All of those things need to be taken into account. So we have a multitude of them. Some of them measure electrical resistivity at the surface. Some of them measure electrical resistivity around the borehole. Some of them measure acoustic properties, nuclear properties, in this case density, by way of sending gamma rays into the formation. And also we can have the possibility of sensing very high resolution electrical resistivity images. So all of these instruments, they measure different rock properties. Some of them measure electrical conductivity, dielectric conductivity, permittivity, Some of them measure elastic properties. Some of them measure nuclear properties. But by combining all of them, then we have a complete picture of the rock. I always say that the magic tool does not exist. There's not one single tool that with one physics, one instrument gives you everything. It's not possible. Right now it's not possible. So we have to combine them in the best possible way. Please bear in mind that these tools can be run while the well is being drilled, after the well was drilled, or even after the well was finished and cased. So we have some of these and possibilities, and these tools and instruments, they can run not only in vertical wells intersecting horizontal layers, but they can also go through high angle wells, horizontal wells. And that's a very important thing. And that's something that it will be very hard to achieve collecting core samples. The other thing that is very important to remember in the context of samples of rocks that are acquired here is that very often the drilling process itself also produces cuttings of rocks. We call these rock cuttings or drilling cuttings. And those are sent with the mud back to the surface and they're collected. So that's another way to sense the rock properties, although not very reliable because these are fragments of rocks that were crushed because of the drilling process, or maybe they have some value, but they do not represent in situ properties. Now, all the logs that we have seen through the several video lectures and also in this lecture, all of those are going to represent multiple physical properties, as I said, acoustic, nuclear, electrical, magnetic resonance, pressure, everything else. So what we do is we integrate those with interpretation methods that we call effective medium theories. And to do that, we have to guide ourselves because fluids and solids, they have different contrasts of properties depending on the physics that one is using to sense that rock. So all of that needs to be glued, if you will, with an interpretation method. We call this interpretation model or interpretation method. And as I said before, those models and methods, they have parameters, and those parameters, they need to be adjusted. The other thing that is very, very important to remember, very important property to remember, is that the different well logs, the different borehole measurements that we use to measure rock properties in a well have different physics, and because of that, they have different depths of investigation, how far into the rocks they go, or they also have a different way to resolve thin layers. So actually what happens is that these measurements make a an average, in space average of the rock properties around the borehole. Sometimes they measure around the complete perimeter of the borehole. Sometimes they measure along a sector of the borehole. And we have density logs that are very shallow sensing and they have high resolution. Then we have electrical resistivity logs that have the deepest depth of radial length of investigation, but also they have the lowest resolution. So in a rock like this, which is a carbonate, we will not be, in some cases, we will not be able to see these laminations and the emplacement of hydrocarbons that we have here, because when you average the properties of these rocks with a large volume, then you're only sensing the combined average of all these properties. You no longer have the ability to sense the individual lamina here. And please note that these holes that you have here are again plugs that were done so that a piece of rock is retrieved, sent to the laboratory for analysis, and that gives us a perspective of or a benchmark of the values of porosity, permeability, and other properties that we have here. So it's very important to understand this volume of investigation that is inherent to well logs. Why? Because the smoothing effect is going to work differently for different logs. Let me give you an example. Let's suppose that you have a sequence of 3 layers here. That's the length. And we have a green layer, pink layer, and a blue layer. And let's say that these layers have different properties. This is the density in grams per cubic centimeter. This one has the highest density. This one has a medium density and lowest density. And then you have a neutron porosity, which measures the hydrogen index or some combination of hydrogen index. Because of different fluids, you will also have different properties and contrast across. It could also be the gamma ray log that has different values going from the rock. And then, for instance, the electrical resistivity, you will have different properties. So that's what you would like to sense. You would like to sense very sharp interfaces like this when you go through rocks, when the logging tool is going through rocks. But you have to remember 2 things. One, the logging tool is moving when these measurements are acquired. And second, each one of the measurements has a different volume of investigation. So in consequence, let's say that the density tool has a certain volume of investigation, is averaging the surrounding properties of the rock with a given volume, and the neutron with another volume, and the resistivity with another one. So then you run these logs, and typically we run them with the bottom up, and each one of these measurements is taking an average of those actual properties. And look at this, the one that is the most better result, it has an average, it rounds off the borders. Look at this, initially the border was very discontinuous, but now it's smooth. It gives us a very good value in the center, but again, it gives us a smooth representation of the original reality. For the neutron log, because the averaging is a little bit, the volume of averaging is larger than the effect of the averaging, or the effect of smoothing of the original properties is more emphasized as shown here. And lastly, for the case of resistivity, that you have also the largest volume of investigation, look at this. We have a severe smoothing of the property of the intralayer here. And because of that averaging, we're no longer able to define the property right here. And that's important because if you're going to do calculations of rock properties from logs that have been smooth, then you have to recognize that the smoothing effect is going to cause inaccuracies at the time the interpretation or the calculations are done with well logs. And here's another example of what happens when you go through very thin layers. This is the resistivity log, the photoelectric factor log, the gamma ray log, and the density log. And what I want to point out is that these green shaded layers, they have one property, and the ones that are white color, they have another property. And look, every time you go through a boundary, the boundary is smooth, and maybe if the layers are very thin, then the property sensed in the center is no longer a representative property, to the point that this degree of smoothing is going to be different for the different logs. Some logs, like the photoelectric factor log, will be only minorly affected by this smoothing effect, but the resistivity log will be severely affected by this smoothing effect. and same with the differences between neutron and density. So it's important to recognize this effect when one goes and compares well logs and core data. Important. And of course, there are other measurements such as borehole images that provide very high resolution images by acoustic ultrasonic images or electrical resistivity images. But these measurements are very slow, they're very expensive, and often they're only run over short segments of the well. So they're not very commonly found. And even if you get this very high resolution, very often we encounter cases where the resolution is not high enough to recognize some of the geological features that perhaps will have an important, significant, measurable impact on the properties of the rocks that we're trying to study. So because of all of that, it's very, very important. It's incredibly important. I cannot use more emphatic words, if you will, to promote the importance of doing core log analysis, core log integration. And here I am with some of my students at the Bureau of Economic Geology. We have laid out core. These are carbonate measurements. Students have the well logs on their hand. And what we're doing here is going through all the pizza boxes here where we have the slab core. And we're trying to look at them visually and understand how the well logs are recognizing the variability that we see in the rocks, and how this variability will give us variability in petrophysical properties such as porosity, permeability, even hydrocarbon content. Subsequently, one can also study the effect that they have on mechanical properties and other geophysical properties. So it's a very important exercise, and that's what I'm going to walk you through with the video lectures that I recorded at the Bureau of Economic Geology. And so eventually you get your well logs, smooth representations of the rocks, all of them, gamma ray, speed, resistivities for electric factor, density, and then porosity and core samples. These are all these triangles, these symbols are core samples taken from plugs that were taken to the laboratory. They allow us to do calculation or verifications of the calculations of saturation, permeability, and do compositional analysis. And then once you do this in one well that has core, once your method and interpretation method has been verified, checked, reality checked with core data, then you know that the interpretation method is reliable, accurate, and then you can apply it in another well that has no core samples, only logs, but because it was verified previously in a well that has core, now you have more confidence to proceed with the interpretation in a well that has no core data. That's the value of this core log integration. And we do it because rocks are often much more complex, much more variable than what we anticipated. This is a piece of rock from Ecuador, and we're seeing lots of variability in terms of genesis, diagenesis, presence of lamina of shell, and look at this, presence of hydrocarbon. But hydrocarbon in these rocks only comes in some sort of a patchy form, only in some segments that have good porosity and permeability. So look at scale, the pen here, the University of Texas pen is serving as scale. Now you can figure out that this rock is varying much faster, at smaller lengths than the size of the pen. And because of that, when the well logs are acquired in rocks like this, the well logs are going to take an average. And how is the average going to work? This is what we call effective medium theory. Well, the average will work in a way that depends on the physics of the measurement. If you're dealing with scalar measurements such as density, gamma ray, then this will be just an average of a volumetric average. But if you're dealing with properties that have direction dependency, such as, for instance, sonic logs or electrical resistivity logs, then not only will you have an average, but you can also sense direction dependent properties such as anisotropy. You will have one electrical resistivity or electrical conductivity parallel to bedding plane, and another one perpendicular to bedding plane. Magnetic resonance, for instance, is a scalar measurement, but it's very interesting because it does pore size distribution, still has a volume of investigation, and that volume of investigation will average the pore sizes that go through the rock. So it's very important to understand this variability and complexity, and because of that, the core log integration process is not only qualitatively necessary but also quantitatively forceful for proper verification of the calculations. So what I'm going to do in these videos is I'm going to walk you through several examples, 3 examples to be precise. First of all, we're going to talk about core log integration with an example of core and well logs acquired in an onshore turbidite sedimentary system. So it's a classic turbidite sedimentary sequence where we have to remember all the elements of the turbidite system, the channels, the crevasse plays, the distal portions of the beds. We have to remember all of these very important concepts of sequence stratigraphy and turbidite systems, Bowman sequences, the effects that they have on the thickness of the layers of sandstone, the thickness of the layers of shell, and also ripple marks and isotropy. All of those things are very important because these rocks are deposited at sea. And when we look at the core for this is actually a picture of a photograph of the core that we're going to look. We have the logs, the well logs, gamma ray resistivities, neutron density, and then we have core plugs. All of these cylinders, the holes that you have see on slab core contained in the pizza box here, all of those are represented here by the circles, the solid circles, each one of them. So they took them, they located them, those are the depths. We match the depths from the logs with the depths from the core. We call this depth matching, and that's how they're plotted. And then we, after the measurements are made in the laboratory of these plugs, for instance, porosity and permeability, then here is permeability and here is porosity. And that's how we display them. And here are the well logs. So the well logs, we have the spontaneous potential, the gamma ray log, the resistivity logs, the neutron density, the sonic log. So when one looks at a channel like this, it's very important to understand what the response from the different logs is going to be, and that this one happens to be a channel right here, and we have stacked channels over here, and then over this part we have a section that is highly laminated because this is the distal part of the fan complex of the turbidite sedimentary system, and we're going to look at some rocks comprised in this segment. Very interesting. And the second data set, the second exercise of core log integration pertains to the Permian carbonate sedimentary sequence. This is in West Texas. We're going to look at core and well logs acquired in the Sacroc field that belongs to Kinder Morgan. And the Sacroc field, if you allow me to do some space representation, is a mound, a reef, a mound reef. I think I'm sure I'm not using the right name, but it's an uplifted protuberance that has carbonate rocks. These are carbonate rocks with very good petrophysical properties. This is the Sacroc field, very prolific field that is being produced by enhanced methods, and one of those methods is the injection of CO2. And this is a cross section of the reef mound complex. We're going to be looking at one of these wells and their logs over here. These rocks at the Sacroc field Permian carbonates, they look like that. You're going to see that some sections have relatively good porosity and permeability. Some other sections like this are very tight, so no porosity and permeability. And because of that, the flow of fluids will be highly controlled by these baffles or flow barriers, and it will be very patchy the way we're going to encounter hydrocarbons in these rocks. very complex carbonates that one can look at them in different dimensions, different sizes. Here are some of the thin sections that indicate presence of dolomites, different presence of dolomitic crystals. There are other sections that are oolite in quality. Some other sections have dolostone, so different degrees of genesis and diagenesis, and because of that, different implications on the flow transport, fluid transport properties, geomechanical properties, electrical properties. All of those things are going to have different responses to the different fabric of the rock. Here is a plot of the well logs that we're going to see in the Permian Basin. This is the gamma ray log. These are the various resistivity logs, shallow, medium, and deep. Then we have the photoelectric factor, neutron and density logs, sonic logs, very important to sonic log here. This is the P wave, compressional wave sonic slowness. Very important to understand where the rock is very rigid, very low porosity, and when it's not. And this in the context of the presence of invasion or differences between deep and medium and shallow allows us to separate the segments, the cycles of this rock that exhibit good permeability. And then here we have the spectral gamma ray logs, potassium, thorium, uranium. And here we have the match between core porosity. Look at the incredible amount of plugs that we're taking on this rock whole core that was acquired along this entire segment, and how the core porosity matches extremely well the porosity calculated from well logs. And here is a plot logarithmic scale of the permeability of these rocks. And you can see that porosity is not extremely variable, but look at permeability. The variability of permeability is incredible compared to the variability that we observe in core porosity. So this is another exercise, visual qualitative exercise that we're going to do, and we are going to be walking through this core with an excellent, one of the most famous experts in carbonates, Dr. Charlie Cairns. Now, the third data set core log integration exercise that we're going to be working with is an incredible example of core and logs acquired over the Eagle Ford Shale. This is a well that is called Cinco Sauces, located in South Texas, very close to the boundary with Mexico. It's a gas field, and we're going to see that the core and logs cover at the top the Austin Chalk. Then we go through the Eagle Ford, the upper Eagle Ford, the lower Eagle Ford. The lower Eagle Ford is the one that has the highest concentration of organic material. This is where most horizontal wells are landed. Then below that we have the Buda Formation, and below the Buda Formation, which is a carbonate rock, then we have the Del Rio Formation. Very interesting sequence, and we also have the well logs that go with that. And here's the gamma ray log. Then we also have the various resistivity logs, neutron density, core porosity, and then core permeability. An incredible example of unconventional rock that we also have to analyze from the perspective of geomechanical measurements, horizontal drilling, the combination of all of that to do the best performance for production. So we're going to look at that's it. And these are outcrops of the Austin Chalk, incredible piece of rock that also produces hydrocarbons in some sections of Texas. There are some locations between Austin and San Antonio that are actually producing in the Austin Chalk. Very prolific formation. And here is the Eagle Ford Formation. This is the upper Eagle Ford. And then we have the lower Eagle Ford. This is the lower Eagle Ford. This is where we have the presence of organic material. If we do a close-up of this lower Eagle Ford, that's the way it looks, the organic material. In some places of some wells in the Eagle Ford, we can find gas. In some places we find condensates and or hydrocarbons with different viscosities. This is the source rock for many reservoirs across, or conventional reservoirs across Texas. And here is a picture photograph of the Buda Formation. And Buda is called Buda because it outcrops in the town or city now of Buda, not far from Austin, south of Austin. And then we have below that the Rio Formation, which is a clastic formation. And then here is another view of the same formations. Incredible variability. And here is the logs, the beautiful photograph that shows the well logs, gamma ray, resistivity, neutron density, spectral gamma ray logs, permeability, and this is the top of the Buda Formation. And then here we have the organic section, the lower Eagle Ford. And guess what? Here the gamma ray log is extremely high, and then we come to this discontinuity. We enter into the Buda Formation, carbonate formation, and gamma ray log drops to almost negligible values. Same we see with the resistivity log, except the resistivity log is plotted in a logarithmic scale. We go from relatively low values to very high values. And that's the reality that we want to see, how this unconformity gets mapped or gets sensed by the different well logs. An example. And this is just another picture of the same transition with the well logs and a pen 4 scale. All of these are pizza boxes of slab core. You can see that the core has been widely studied. All of these numbers are different testing and procedures and studies, laboratory studies or geological studies, thin sections, etc., compositional, the X-ray diffraction tomography, all of those measurements were performed right here, and these numbers are identifying those experiments or measurements all over the place. So that's what we have ready for you. So I'm going to walk through all of these with you. We have the exercises, we have the experts. I videotaped all of these at the Bureau of Economic Geology. And in summary of what I just said, well logs are excellent primary data of information for compositional, petrophysical, mechanical, all kinds of properties, geophysical properties. But they have limitations. The volume of investigation, the smoothing that they have. So because of that, it's very important to reconcile them with high-resolution measurements, either high-resolution borehole measurements or core measurements, or integration with core visually with core samples. And it's very important that because of the variability or the smoothing, the differential smoothing that we have from all the different well logs, that when we do interpretation methods, those interpretation methods be calibrated properly, be reality checked properly with core measurements, with core studies, so that the interpretation is reliable and accurate, and therefore that can be applied in wells where we don't have core data. And because of that, now you see that not only core and well logs are complementary, but in cases where you have rocks that are extremely complex and extremely variable in space, then it's very important to verify the calculations with core data. And my super important suggestion is that look at the rocks before you do calculations. Understand what kind of complexity of rocks you're dealing with before you start plugging numbers on user-friendly software. So having a great piece of software or even a great piece of machine learning, artificial intelligence software is never going to be a substitute of looking at the reality presented by the rocks. Very, very important. And with that said, this is my last suggestion, recommendation, is that when you're trying to do analysis of any kind, petrophysical, compositional, geomechanical, you name it, you have to understand the rock complexity. And it's very important to look at any possible direct indication of properties of rocks, be it well logs, be it outcrops, core samples of drilling cuttings that come from the drilling process. All of those provide reality check verification for all the calculations and interpretation methods that combine multiple well logs. And here I have a few review questions. These are just important so that if you want to go back to after you review all these lectures having to do with core log integration, whether you understood the main concepts properly. With that said, I want to thank a number of people. First of all, I want to thank Charlie Cairns from the Jackson School of Geosciences. Excellent colleague, excellent expert, great person. He came to walk with me through all of these samples of the Sacred field. I also want to acknowledge Dr. Toti Larsen, another excellent researcher at the Bureau of Economic Geology, who helped me walk through the Eagle 4 core with logs. I also want to thank Dr. Jerry Lucia, a great colleague, for some of the plots that I'm using for the Sacred field. I also want to big thanks to the Bureau of Economic Geology. I'm associated with the Bureau of Economic Geology, and essentially they provided their facilities for the core log integration exercise that I video recorded. So my heart goes out to them. I thank them because of their excellent support during a difficult time when the recording took place. And lastly, I want to acknowledge the support from the Hildebrand Department of Petroleum and Geosystems Engineering, because it was through one of the grants from the Hildebrand Department that I was able to pay for laying out the core at the Bureau of Economic Geology, having it ready for us to go and analyze it. And with that said, let's go now for the next segment of the lecture. We're going to walk through the turbidite sedimentary sequence. We're going to look at logs. We're going to look at basic properties of core log integration, and then carbonates, and then Eagle 4. So let's do it. Have a great time. Thank you.